I'm going to put record on. Can you guys hear me? I'm going to ask you on the chat. Oh, yeah. Okay, good. Excellent. Because yesterday, for some reason, my students couldn't hear me. The microphone wasn't working. Okay, it's good. Okay, I put up some stuff. I didn't put up questions from last week. If you remember, we talked about, you know, the parts of a communication system. And I said, when you look at communications, you're dealing with, first of all, creating the message that you're sending. So you start out with voice, and then you need to, or with a picture, a movie, then you need to encode it and make it like JPEG or MPEG, whatever format it is. So that's encoding. And then you're doing error control coding. We're not going to get into that. And then you modulate it to actually send it over a channel. And the middle part was the channel. And I said the channel is the part which is a problem. Like this is just inserting all of the noise and error and everything that you are going to have to deal with. And then the receiver has to get that signal back and figure out, you know, what the bits are. But even before that, is there a signal on this channel, right? That's, you have to figure out if the signal started, when exactly it started, so you don't miss the first few bits or something. You have to have all those synchronizations in place. Demodulation, decoding, and then, you know, decoding the source coding as well. So we were talking about the first part of this, the source coding, if you recall, and I talked about this Huffman coding. So the idea with source coding is that you have some information, like suppose I'm sending this slide. When you show this slide, if you look at the file, it has these words as text, right? And then it has a design for the slide. So this is source encoding. You're not trying to, you know, get every pixel that's to be drawn on this screen. Instead, you're going to tell the computer how to draw this, and then the computer draws it. That way, you can have a much smaller file size. And if you need to send it somewhere, you're going to send fewer bits, right? So you might be familiar with things like the zip algorithm. When you rar things, that's source coding. So the types of codes that you use, and entropy, if you remember, is basically how much change there is in your signal is the entropy. How the bits are, how many differences are there in the bits? Like how different are the bits from one, you know, one symbol that you send to the next one? It's just a measure of, and then that's also a measure of how few bits you need to actually store this information. You can calculate it quite easily using the formulas. Probability of getting this bit times log 1 over p, probability of getting the second bit times 1 minus, you know, times the logarithm of 1 over 1 minus p. That gives you your entropy. So the highest entropy is for things which are very unknown. That would be when you're receiving a bit and you have no idea if it's a 0 or a 1. Probability 50%, it's 0. 50%, it's 1. High entropy. But if you have a signal like the burglar alarm, where most of the time it's 0, sometimes it's 1, what would you do? You would only transmit when it's a 1, right? So that way you have a very low transmission rate, right? You need a very low rate, reliable connection for a burglar alarm. So yeah, so that would be a very low entropy signal. We have ways to, like, it's easy for a burglar alarm because it's 0, 1, right? But what if you're trying to compress an image? And how can you do that? And how many bits do you need for that? Okay, so this is where you have these algorithms. So one of them is called Huffman code. Oh, hello. Yes. What are we talking about? Communications. Oh, I'm so sorry. Yes. Thank you. I forgot to share my screen. Okay. Well, thank you for reminding me. We're up here. Okay, so I was looking at the presentation here. Okay, so we're talking about communications. Okay, so we started last week. These are the slides from last week. I'll do electronics next week, just a little bit of electronics. But I've changed this. I'm not doing embedded system. I'm actually doing networking here. But anyway, you have these slides. So we talked about this, and we left off at entropy. I explained entropy last week. Okay, and then I said source coding. So like the algorithm for zip coding, when you have a file on your computer and you do zip coding, that's source coding. When, you know, PowerPoint is saving this as a file type, that's probably got some source coding, right? So the idea is you have these pixels to send, right? This image to send. How do you use the fewest number of symbols to store it and to send it? And there's a measure. It depends on, see here, probabilities are very high that it's a 0, right? Most of the time I'm sending a 0. Sometimes I'm sending black. So most of the time I'm sending white. Sometimes I'm sending black. Some of these pixels are black. And then there's one pink line, right? So there's only 3 colors. So I don't need to use RGB, you know, the amount of red in each pixel, the amount of green in each pixel, the amount of blue in each pixel. That would be a waste of space. I could just say there are 3 colors, and I could send for each pixel, I could write down it's white, or it's black, or it's pink. You'd need 2 bits to write that down. 0, 0 would be white, 0, 1 would be black, 1, 1 would be pink, for instance, right? But you can do even more than that. You can say if it's a white, I just won't write anything down. Maybe by default, everything's white, right? So then I only need to write something like a pixel for, like a bit for black. So here is a better coding idea. When it's white, I got to write down something, because otherwise I have to give the location for each pixel, right? When it's white, I'll write down every pixel, but when it's white, I'll just write down 0. 0 is for white. When it's black or it's pink, I can write down 1, 1 for black and 1, 0 for white. I have to write down 2 pixels whenever 2 numbers, 2 bits, whenever I have a pixel that's black or a pixel that's white. But pink, a pixel that's black or a pixel that's pink. But for white pixels, which are the majority of the pixels, I only write down 1 bit, and that's a 0. When you get to a 1, you realize, oh, this is 2 pixels that give me the color, so it's 2 bits that give me the color of this pixel. Okay, so this type of coding has a name. Somebody thought of this. It's called Huffman coding. And they can do it for more than 3 colors. So what they do is they look at the source letters. Now, in our case, the source letters were white, black, and pink. For every pixel, I'm sending white, black, or pink. And then I rank them in probability. So P1 is definitely going to be white, the probability of having white. You look at all the pixels, find what percentage of them are white. That's P1. And then you look at all the pixels, find what percentage of them are black. That's black divided by all the pixels. That's P2. And then look at what percentage are pink, right? That's the fewest number of pixels are pink. So the P3 is going to be number of pink pixels divided by number of all pixels. Then you assign 0 to the last digit of AK and the 1 to the last digit of A minus 1. So, what is it, AK? I would say A1. I would P1. So the symbol that corresponds to the largest probability, I'll give it a 0. And the next one, I'll give a 1. And then what I do is I combine PK and PK minus 1 to form a few probabilities. Okay, so what I'll do is I'll do this for you for my example. I'm sorry, I forgot to connect up my writing pad. Just hold on there. And it's like, I'm going to use PowerPoint, but okay, here we go. So for instance, suppose we have an alphabet where we have white. Didn't work. Try again. We have 3 symbols. Some pixels are white, some pixels are black, some pixels are pink. And suppose of all the pixels, let's say 9 out of 8, like say 8 out of 10 are white. Let's say 1 out of 10 are black, and 1 of 10, I'm just making up these numbers, but 1 out of 10 are pink. Okay, so I need to encode this sequence, like this message. Okay, so these are the AK. Okay, so A1 is white, A2 is black, A3 is pink. And the probability of getting white is P1. This one is P2. This one is P3. And look that I've actually ranked them. Maybe I'll even change this. Make this 7/8. Okay, so I can rank them in probability. 7/8. This one is 7/10, 2/10, 1/10. Okay, and this is decreasing probability. Okay, so I kind of write these down and say 1, 2, and 3. The probability of having symbol A1, I'll just write A1, A2, A3. The probability of having this A1 symbol is 0.7. This probability is 0.2. This probability is 0.1. Now I look among all of these and find the two smallest that I can add. Okay, so I can add A2 and 0.2 and 0.1. When I add these, this becomes 0.3 versus 0.7. I've kind of come to the end of it, then you can't add anymore. When you add these, you'll get 1. Okay, I'll do a longer example in a few minutes. So this is the way it works. You assign a 1 or a 0, it doesn't matter, to the top part, and then the opposite to the bottom part of this, and this becomes 0. And then you assign like a 0 here and a 1 here. And now you can read off the code to get, if you see an A1, you should encode that with a 0. Okay, if you see an A2, you should encode that as, I'm going the wrong way actually, to get to go from this direction. To get to A2, I'm going through 1, 0. 1, 0. And for A3, I need to go this way, pass a 1, and then I pass a 1 again. So A3 should be represented by 1, 1. So how many bits did I use? Well, if I have a symbol A1, I only need 1 bit to give this information. If I have symbol A2, I need to send 2 bits or write down 2 bits on my file. And if it's A3, I need to write down 2 bits on my file again. Right? So what is the average number of bits in the file? If I had a file with, like not bits, symbols. How many bits would my file be? If I had a file where I had like 500 pixels, 1,000 pixels, how many bits do I need to write in my file? How big is my file going to be? Well, we'll see it this way. I'll have 1 bit 0.7% of the time, right? I'm sorry, 70% of the time. With probability 0.7, I'll get a 1. And then if I have one of these two symbols, I'll have to write down 2 bits. So all the symbols for 30% of those symbols, or 0.7 of those symbols, I need to write down 2 bits. Right? So on average, I'll be writing down 0.7 plus 0.6 would be 1.3 bits per symbol on average. Now you think of it this way: if I had 1,000 symbols that I want to encode, about 700 of these would be 1 bits, because they'll be white, right? Roughly, okay. So 700 bits for the whites. And then for all the pixels that are black and pink, there are going to be about 300 of those. I need to write down 300 bits. Right, so if I have 1,000 symbols to encode, okay, about 700 of them will be white, about 300 of them will be black or pink. They'll need 2 pixels. I need to write down 1, 0 and 1, 1, or 1, 1. And then for the white pixels, I need to just write down a 0. So I would have a total of 1,300 bits. I will use 1,300 bits to encode this image. Okay, so if I had even more whites, you can see what's going to happen. This is going to go down. If it was all white, then I guess I would send 1,000 bits, or I could just send 0 bits, right? Because they're always white. I don't need to send anything at all. You have 0 entropy for that case. Okay, so let's do an example with this. I haven't quite worked out their method, but I'll do an example the way I know how to do it. Okay, so let's do this new problem. I have 5 letters in my alphabet. Okay, the probability of, oh, that's the answer. Go back to the question. Oh, okay, so this is the question. This part's the question, right? I have 5 letters in the alphabet, and the probabilities are given here. And I need to find a code to transmit these. Now, with the code, of course, the transmitter, the transmitter and the receiver have to agree as to the code, right? The receiver has to know that if it's a 0, I meant a white pixel, and if it's a 1, 0, I meant a black pixel. If it was a 1, 1, I meant a pink pixel. The receiver has to know this, or when you're reading the file back, you have to know this. You have to have the right program to read and display the file, right? So that's important. There's some communication, setup communication going on. And then you can go on to doing this. Am I recording? Okay, I am recording. Okay, so let's do this example. Now, these are nicely ranked as well. See, 0.3, 0.25, 0.25, it's decreasing. Okay, decreasing order. Okay, so again, I draw the same diagram. I have A1, A2, A3, A4. This is going to be a little trickier because when you add them together, they become a larger number, right? We'll see how big they get. 0.3, this one was 0.25, 0.25, 0.1, 0.1. Now look at these. These are the smallest. Obviously, the first thing we'll merge is these two, and they'll be 0.2, right? And then it would be easiest probably to merge these two, and you got 0.45. Now the smallest two are the 0.25 and the 0.3. So now we merge these two, and we get 0.55. Okay, and then of course they both add to 1. Now you can give bits. You can do 1, 0, and you can see there's more than one solution. Like I could have, here I merged A4 and A5 with A3, but I could very well have merged them with A2 as well. You could come up with a different code. So there's more than one Huffman code. So this is a Huffman coding example. Okay. So what will we do? Let's and then again you make a choice. This can be 1 and a 0, or it could be 0 and a 1. It doesn't matter. And every time I come to one of these crossroads, I give one end a 0 and the other end a 1. I'm just gonna do it like this time. And a 1 and a 0. Okay. So now I can write the symbols for each of these, the bits for each of these symbols. Okay. So for A1, whenever I see A1 in my message, I'm going to go and I'm going to write 1, 1. Whenever I see A2, I'm going to write 1, 0. Exactly, good job. And then A3 is 0, 1. Yep. How about A4? 0, 0, 1. Excellent. Good job. Good job, guys. A5 is, oh, there's people listening. I'm so happy. And your A5 is 0, 0, 0, right? So when you look at this, it is uniquely decodable. If I wrote a whole bunch of 1s and 0s, I could decode it. Anytime I see a 1, it'll be A1 or A2. And then the second bit determines if it's A1 or A2. And then if I see a 0, it must be one of these. Right? Because this path is kind of unique for each of the symbols, you can uniquely decode any message here. Okay, so it's a perfect encoding. It's called a lossless code. Not lossless. Lossless is supposed to be spelled together. Source code. And this is what you would use to transmit, for instance, your files, executable files, right? Because having lossless files is very important. What is this? Okay, lossless files is very important if you have executable files or something. But when you're transmitting video and you're transmitting sound, it's not the same, because for video and sound, you're going to you're transmitting to a person, and people don't see every little detail. So actually, you can have lossy coding. Huffman codes are Huffman codes. There's another algorithm called the Lempel-Ziv algorithm. Coding. This is what we know for zip files. It's more complicated. I don't want to get into it. It's because there you have to come up with the alphabet using the file, and then using that alphabet you encode the file. So it's a little Lempel-Ziv is a bit tricky. It took me a while to learn it. But lossy coding is source coding. Examples of this are JPEG and MPEG. JPEG, MPEG, the MP3s, anything really. Because you're going from the analog to digital domain for a start. But with MPEG, with JPEG, you can actually encode it so that if you don't have enough bandwidth, you've seen YouTube, it goes down in terms of resolution, right? So it's losing bits all the time. You just want it to be good enough for a person to be able to recognize it and to be able to communicate. Other than that, people like it when there's more resolution, but they can do without it. So these are lossy source coding algorithms. No, doing coding. I tried to write coding. What do I? Coding algorithms, and many of those are used for humans. And then if you're trying to actually transmit something from a machine, like a program, then you'll use lossless source coding. Okay. Okay, so that's Huffman coding. You understand how that works. So that's source coding. Next stage, we're going to talk about. I've got some sources here. I have two kind of things that I wanted to talk about. One thing we can talk about is propagation and this stuff. I didn't quite finish these slides, but I have more slides other places. Yeah, let's stick to physical layer. I might get into networking a little bit if we have time. Okay, so communication. So we talked about this, communication channels, blah, blah. Okay, so communication channels. I said the channel is the part that's really difficult, right? So this is the part that's going to introduce error into your system. What kind of channels do we have? We have wireline channels. That's your Ethernet, right? But also, cable that comes in with a cable and fiber optic cable, waveguides, and so on. And then we have wireless channels. And these can be very different depending on, for instance, the environment. Inside a city, there's lots of reflections. In a room, there are many objects. So the signal is reflecting, running into things, going through things. That's very different from transmitting in the middle of a suburban environment, in the middle of a field, right? And also, the propagation characteristics change, like how much signal you get and how much that signal varies in time. Because if you're in a place where there are fast-moving vehicles and things, your signal might be good 1 second and then it goes bad. Okay, so the gain changes a lot, and that can also depend on the frequency as well. And we're transmitting from the kilohertz range. I guess mostly walkie-talkies are in the kilohertz range right now, to ultraviolet, right? You can transmit information using light. So yeah, it depends on frequency. It depends on the environment. It depends on the antenna. And multiple antennas are a big thing now, right? Massive MIMO. I'll show you some at the end. I have some slides for that. Okay, so when you're transmitting, most of the communications we look at really are space waves. Although technically, there are things called ground waves, which propagate close to the ground. And you can see that the way they've drawn it, they show how it's like bending with the curvature of the Earth a little bit. And that allows you to go a distance, because most transmission is limited by the curvature of the Earth. If you're too far away, if your transmitter is on this end and your receiver is on this end, it will have to go through the Earth to get to the receiver. That's not going to happen, right? That's all rock. It will block any kind of electromagnetic signal. It's difficult to get a signal even through water, right? There's always something Why? Because of conductors. Remember about conductors? They won't, because they just conduct away essentially the field, the electromagnetic field. Using the electromagnetic field to communicate, the conductor just conducts it everywhere else, and it doesn't go into the conductor. That's why you have a Gaussian surface, right? So ground waves, though, are the bits of the waves, they kind of stick close to the ground. Why? Often they reflect off very low clouds, fog, things like that. And they just, you can think of the ground as a giant conductor. So they kind of go that way because of that. But it depends on the frequencies that you're using. Space waves are most communication today. You just go through space. It doesn't go very, very long distances anyway. And then there's also sky waves, which were used in the first years of radio, even up to past the Second World War. Into the 1970s, if they had a ship in the middle of the ocean and it was trying to communicate with land, they would have to send a signal. It would reflect off the upper layers, the ionosphere, and then the receiver would get the signal. And of course, after that, in the 80s and 90s, we all used satellite communication, mostly. If you wanted to call America, what would happen? Your signal would go to a satellite, and then it would be beamed back down again. So intercontinental or like international communication was very expensive because you're using up time on a satellite, right? Which is the highest technology back then. And also it was very laggy because it actually takes a long time for the signal to go up and then go all the way back down again. So these were the different modes. Now, nowadays, we use space waves, go to the base station, and then everything is conducted using Ethernet, some other form of internet, to get to the receiver, right? And then to get to another base station, and then you communicate using over the air again. So we have way more wireline communications, and we have the internet going down through cables everywhere. Like there's cables everywhere, right? Okay, so propagation characteristics. This explains these a little bit. It's not so important. Generally, we give them names. At the beginning, there was low frequency, LF, medium frequency, MF, and high frequency, HF. Right? So they start off with the low frequency, and then they went, well, this is medium, that's low. And that's when they named these. Now, once they had named low, medium, and high, it became difficult when they were using other frequencies, right? So they went, I'll pull this back. Sorry about the alarm. Anyway, so when they were like, we're going to use lower frequencies, then they gave this the name very low frequency. And this one is extra low frequency. Okay, the very low frequencies are used mainly for things like submarine communications. Someone said something. Hold on. Yeah, I know, right? They're just coming up with names at this point. Yeah, but those are used mainly for submarine communications because the signal does not propagate very well through salt water. Salt water is a conductor. You send the electromagnetic signal and just the energy, the wave dissipates everywhere and it doesn't get to your destination. Time signal navigation, some of these low frequencies. If they're communicating, I've seen them used for communication into mines underground. Again, those communicate better when the medium frequencies don't. As a general rule of thumb, low frequencies are like sound. They will travel through anything. Like they will travel through walls. You close the door, you can still hear someone, right? Whereas very high frequencies are light. So when you close the door, you're blocking most of the light. They can only go through open paths. So anyway, so now they had low, medium, and high, but then they started using higher and higher frequencies. So again, this is very high frequency, ultra high frequency. I believe that's super high frequency. I'm not sure what the E is. Extended high frequency, extra high frequency. Yeah. So now, so what happened is cell phones, when cellular systems started, they were in the 900 megahertz band, right? That would be UHF band. And also we had 2.4 gigahertz Wi-Fi channels. Okay, so those were in this band, ultra high frequency band. Now, if you ever looked at your Wi-Fi router, many of you have Wi-Fi routers working at 5 gigahertz, right? We're in super high frequency range. In fact, these were used so little, I'll tell you, the microwave ovens work in around 2.4 gigahertz. So they often interfere with Wi-Fi networks. But 5 gigahertz doesn't seem to have that. Some satellites, microwave links, telemetry, and so on also use the 330 gigahertz. Now they're planning to use 60 gigahertz for communications. You know, with 5G communications, they're going to have those hotspots where they transmit a lot of information. That's going to be in the 60 gigahertz range. So that falls into this extra high frequency range. We're going higher and higher in frequency, and we can do this for a number of reasons. Number one, the electronics has gotten, our skill at making electronics has gotten a lot better. Initially, when we were making these things in the lab to work at 2.4 gigahertz, it was like art form. You know, my advisor, my PhD advisor, my professor hired this guy who worked on radio. They worked on those giant things they have for antennas for looking at space. So he was the engineer for the local space thing, telescope that was close by. And he hired him for a month during his break, so he would come and design the 2.4 gigahertz transmitter receiver that we were using. And it was very hard to design it. And in terms of circuits as well, the production was also a problem initially. But as those things improve, the production techniques improve, and the technology improves, then you can actually make stable transmitter receivers that you can produce that work in these high frequencies. Right. So that's yes. Yeah, I know, right? Yeah, he was this guy, like he didn't even talk to us. He'd just go to his lab and he was working on these components. And the components were big because, we're buying them from the catalog. And, you can't use wires. You actually have to use these tiny waveguides for that. So he had like a bunch of waveguides just screwing things in. Don't touch this. It's in some corner of the lab. Like no one go near that corner. Each component costs like $2,000. It's very expensive stuff too, high frequency things. But it's always more expensive when you are making your own stuff. It's always less expensive. Yeah. So it's always less expensive when you're making it in bulk and you can sell cell phones and things like that. This is getting in the way of me seeing your chat. Okay. Okay. So now we've gone up in frequency. So now that was 2.4 gigahertz. So now we're communicating at 60 gigahertz. I'll tell you my 60 gigahertz example. I used to live in Seattle, and in 2000, roughly, when they had when everybody started getting internet to their houses, there was this company called Rocket Link. I'm pretty sure it was called Rocket Link, and they were going to use 60 gigahertz frequency to give internet to the house, like apartment buildings, like people who lived in a very small area in downtown Seattle. Right, and so people were very excited about this. You don't have to get the cable internet. You don't have to get internet from your telephone. You can hire these guys, and they will beam the internet directly to your house. And they did have a plan. They had a plan to make it go close to the building, so they weren't actually going out into, because it's harder to send it across between buildings. The only problem is Seattle is a very rainy place and very cloudy place. There's a lot of fog. And 60 gigahertz was dissipating in the fog. So they would have so many outages. So first everybody was so excited and signed up for it. And then like everyone was complaining, oh, I got this rocket thing, it's terrible. It goes down all the time. Anytime there's some mist, I can't get any internet. So it was like they had a lot of problems with it. But with improvements, particularly in multiple antenna technology. So what they've done now they're going to use 60 gigahertz. So why isn't it going to disappear into the rain? Because they're going to use multiple antennas, many different antennas, all working together. They couldn't do this in 2000 because the RF parts, not just the antenna itself, everything, all the circuits that feed that antenna are quite expensive. So they had to have many of these in order to have one link that didn't go down. But the thing is, each of those costs, like I said, maybe $1,000 to make. So like it would make the whole circuit very expensive. So they had like single antenna links, and these links just went out all the time. So now they're going to use 60 gigahertz, but with many antennas. In fact, massive MIMO is what we call it. There are a massive number of antennas for a single or for multiple links, but the number of antennas is going to be bigger than the number of users. So that's the plan. The base station will have like 500 antennas, and then they expect that base station to only have maybe 100 users. So then you can have 5 antennas per user, and also if the user is close to the base station, it's only going to need 1 or 2 antennas. But a user which is far away from the base station might use more of the antennas, right? So this requires a lot of intelligence inside the circuit, deciding who's going to get use of which antennas, how they're going to be used, all of that. It requires a lot of RF. You've got all of these antennas, and then they have the analog circuitry to feed them, and all of these things. So that's why as technology improves, we increase frequency. Also, why do we want to increase frequency? Because think about it. If you are at 300 kilohertz, your signal is going to be 1 kilohertz bandwidth. That means that you can't transmit very fast. You can transmit 500 symbols per second, right? Which is small. It's 0.5 0.5 kilobits per second. That's your transmission rate. Assuming you use BPSK, but yeah. But if you go up to 30 gigahertz, like 60 gigahertz, you could have 10 gigahertz. Not 10 gigahertz, but 5 gigahertz or 2 gigahertz. Like that's gigabits per second speed, right? So yeah, you can really improve your transmission speed by increasing your bandwidth. Each signal is given more space because there's more space in the higher frequencies. Okay, this is actually the US frequency allocation. I put up the figure for this as well last week. You can't see anything here, but this is going from 0 kilohertz back down here all the way up to, I'll show you the PDF file. Still can't see anything. But it's going from 0 kilohertz over here all the way up to 300 gigahertz over here. And it shows you this is a plan of how the US uses all the frequencies. So they decide for each block what's going to happen on that block. Are you going to do broadcasting, radio broadcasting here? And you have, I don't know, mobile communications, maritime mobile. This is for ships. So look at this. There's like a very detailed plan, right? Aeronautical radio navigation, planes, right? Broadcast FM radio. So all of the frequency is basically divided among different applications. And there's a frequency. It seems more like compressed in this area, but you also have to realize this area has more bandwidth. So they've kind of compressed, like this is 1,610 to 1,670 gigahertz, right? Is it? Yeah, I know. This is 84 to 86 gigahertz. That's 2 gigahertz right here. Whereas the entire line, the first line goes from 0 hertz to 300 kilohertz, right? So it's kind of compressed as you go down. But yeah, so this plan is actually kind of international. Someone said something. Nothing? Okay, yeah, so this plan is actually international. And I put down the link here for the Turkish thing, but it's not, they don't have a nice figure like this. But because through the International Telecommunication Union, and they basically all get together and decide, okay, we'll all allocate this area. There's some changes between countries, but they're not huge. Okay, so make this small again. I feel like someone must have written something, but I get the sound that somebody wrote a message, but that every requires special measure. Is what it told us every. Well, they have a special topic for every frequency. Sorry, they have a special topic for every frequency. I didn't see your message at the beginning. Like they allocated according to, and of course there's like groups that come in for the. I'll give you one example for reading electric meters, because apparently the distribution companies, the electrical distribution, gas distribution companies, to be able to remotely read your electric meter, your gas meter, in some countries or in some areas, they can do this, but they usually use the telecommunication network. They usually use cellular networks. And of course, they have to pay some money to the cellular networks in order to, and then put like a little GSM card on it. and that way they can read the data at a central location. But they're not happy about this. They want to be able to read it for themselves. So they lobbied to have a certain frequency allocated for metering. I don't know if this, I don't even remember what the frequency is now, but it's a very low frequency in the kilohertz range. 1,200, 1,300 kilohertz. There's one small amount which is for metering, small like frequency range which is supposed to be for metering, and yeah, they are lobbied to have that frequency range allocated so they could set up their own communication network in order to read the gas meters and the electric meters directly and not have to use the cellular network to do that. So yeah, and of course, cellular companies are always lobbying to have more bandwidth. Broadcast television is pretty much dead. I think this is an older app. This is broadcast television, but nowadays, this is not digital. This is analog television. Analog television has ended. So there was a lot of argument over who was going to get. Yeah, this might be actually where they put that metering part in the old television area. And the reason that they want to use the low frequencies is because they travel very far. Like I said, sound travels through walls, but light doesn't, right? So they can have this meter in an enclosed space, hopefully not too far inside the building, and then they'll be able to read it from there directly. Okay, so yeah, so this is the frequency map. You can look at this. Some of these frequencies you're allowed to transmit on without notifying your government authority that you're transmitting, but most of them are actually heavily restricted. You're not allowed to transmit there without the government's knowledge. Okay, so when you're transmitting, and this is a general thing that I'm going to refer to in electronics as well, the antenna size that you need often depends on or it depends on the wavelength, not the frequency wave, the time wavelength, but the spatial wavelength of an electromagnetic wave. So in communication and in many applications, you're transmitting a version of a sinusoid, right? And the sinusoid has a frequency. You know, if you look at if you just measure the electrical signal using a voltmeter, the amplitude will go up and down sinusoidally, right? So we all know this, but what many people don't realize is that there's also a spatial component to this. In other words, when you're sending, the simplest example is the power waves, right? Power line, the 60 hertz signal that's coming out of your electrical outlet. When you see 220, so what's that doing? The 60 hertz outlet, it goes from, it's not 220, but positive V to negative V. I'm not going to calculate it now. Positive voltage to a negative voltage and back up again, right? So when you're at peak positive voltage in your house, it is actually not the same voltage outside. It forms a spatial wave along the wire as well. So at some part, like you can kind of draw this thing across the voltage on wire at time t0. So I take a snapshot of the voltage across this wire at every instance of time, and I'm connecting this to an oscillator. Okay, there's also ground here, but don't worry about it. I'm just trying to generally give you. There's an oscillator. There's a voltage. The voltage is here is just constantly going up and down. It's oscillating. You're driving what's the connection across this wire. Okay, I'll make a circuit of it, so just so it doesn't look ridiculous. Make this an oscillator, and of course you have some kind of load over here, a load resistor here. There you go. Let's make this a circuit. Okay, so this is a sinusoidal source. So I'm running a sinusoidal source that could be the output from a power plant, right? And when you look at this voltage across this wire instantaneously, you'll find that some places are showing positive V, some places are at negative V, some places are at 0. at any instant in time. And this applies also to the any chip, like small device. You're using your CPU, all of the chips inside your cell phone, they also have wires on them. Most of the time, they're also driven by oscillators. They have cosine or sort of similar waveforms transmitted. And yeah, they also, at some instant, they have plus 5 volts. And so when you look 2 millimeters down that wire, you'll see negative 5 volts, right? So usually we require, we would not like this to happen. Now, this happens when you're transmitting energy or electrical energy from one end of the country to the other end. Okay, because when you look at 60, so what is this? Like, first of all, we might be interested, what is this? What is the length between here and here? What is this length, lambda, across which this voltage varies? Well, there's a simple formula for it. You can calculate it. Lambda is c divided by f, where c is the speed of the electromagnetic wave across the wire or the air or wherever, generally the speed of light. Might be slightly slower, depending on the thing. You will learn about that in electromagnetics class. Let me open up. Yeah, wavelength. Yeah, exactly. Lambda is the wavelength. The spatial wavelength. Because when you say wavelength, sometimes we think, oh, well, in time, it's varying in time too. Oh, okay. It's varying in time too. No, this is the spatial wavelength, right? So here it's talking about, what is this? This is a 30 gigahertz. These are 300 gigahertz, right? 300 gigahertz signal. It's at the top end of that. So if you had a 300 gigahertz signal and you divide C divided by 300 gigahertz, you would get, well, this is wrong. You don't get 10 to the 5. This is kilohertz, right? Let me correct that while I'm here. I'm obviously trying to connect by a 3 kilohertz signal. Yes. But this actually brings up an important point, because if you're talking about the 3 kilohertz signal, the size of that wavelength is 100 kilometers. So you can see that's very, very long, right? So on a typical circuit, if you have a 3 kilohertz, on typical circuit, if you have a 3 kilohertz signal across the circuit, then you don't need to worry about it, because you're not going to have a 100 kilometer long circuit, right? But with 60 gigahertz, that can be a problem, because sometimes you transport energy across, like, kilometers, hundreds of kilometers. Plus, you're not just interested in maybe, one end being this voltage and the other end being this voltage. You might even be worried if you got half that length, right? Because somewhere it's 0, somewhere it's 1, somewhere it's 0 again. What's going on with this? And it's, yeah, you'll also be radiating some of your energy out as well. But okay, but if you have a signal which is very high frequency, which is what we're trying to do, we're trying to look at gigahertz signals. So what if it's 30 gigahertz? That'd be 3 to the 7th power. Well, that means it's 10. Oh, it's 10, right? 10 meters. And then if you have circuits, like this is your transmission velocity. What if you had a circuit at terahertz, what if this was 3 to the 10th power? Right? Then you have 0.02 meters. That would be 2 centimeters. Now you might have a circuit that's 2 centimeters in size, right? So, and like I said, it's not even the 2 centimeters. Even if the voltage across one of your circuits is varying partway, like it's going a quarter of this, or just even a small part of this, this becomes an issue. In fact, there is something, kind of diving into electronics right now, but there is something called the lumped circuit assumption. In other words, everything that we learn about resistors, capacitors, inductors, they only work if you are sure that when you have this cable connecting two components, or this is the size of a component, if the voltage here is equal to the voltage here, they have to be equal. or just very small difference between them is allowed. They really have to be equal. So you really need this to be like the circuit to be less than 1/100th of the number that we're finding here. And if you can assume that the circuit is a lumped circuit, if you can make this lumped circuit assumption, then you have resistors, you have inductors, you have capacitors, and you can just use the circuit theorems that you're going to learn, and easy circuit analysis works. But as we are increasing our frequency, our speed of the speed of our circuits, in order to increase what? To increase the computation time, right? To shorten the computation time, you need the circuit to work faster, right? So your computer runs faster. But what that means is you have a higher frequency for your CPU. And then you get to the point where you can't make the lumped circuit assumption. So for some circuits today, when they're designing VLSI circuits for communications or for like, image, even CPUs, things like this, they can't use this regular circuit theorems. They have to do electromagnetic modeling of this system, because a wire is not a wire. The voltage is changing across it, right? So this is a very different world in that case. Anyway, so that's the electronics part of this. But the communication part of this is, when we have an antenna, which is a multiple of this 100 kilometers, or 20 centimeters, when we have an antenna which is a multiple of this, or even lambda over 2 or lambda over 4, exactly 1/4 of this antenna length, of this wavelength length, the wavelength, then you can transmit signal more efficiently. Because the way you will learn this again in electromagnetics class, perhaps, it allows you to transmit the radiation out, but some of the energy actually gets reflected back down the antenna, back into your circuit. And to prevent that, you want the length of the antenna to match the wavelength of your signal. Right? It has to be like 1/10 or 1/2. And a lot of the time, bigger than 1/10. Now, how do you do this? Well, it depends. Sometimes you can have a smaller length, but also one thing they do is to wind the antenna. Like the antenna wire is actually long, like 22 meters long, but they wind it around, a conductor in such a way that it does work. On the PCB antennas also, you'll see a lot of PCB antennas that look like this. Okay, so the length of that spiral is actually proportional to the lambda, and also these turning points are also chosen in a special way so that they can get maximum sort of benefit, so that the signal's not coming back into your circuit. It's just radiating out away from your cell phone. Otherwise, you're just wasting that energy. Okay, so the wavelength in space is where were we? Is lambda is c divided by f. C generally the speed of light. Why do we need modulation and demodulation? Again, why were we modulating again? Frequency assigned multiplexing. We talked about this. Do I need to get into this? The idea is, yes, frequency characteristics of antennas are different. I don't know, antennas, atmospheric, cable properties. Yeah, like I said, you need a smaller antenna at higher frequencies, so that's helpful. And you can reduce noise and interference. Noise and interference. We're kind of going to get into that a little bit. Getting into that a little bit. I'll talk about that in a while. Multiplexing, to have multiple users transmit at the same time, and then you can use frequency assignment for different applications and for different users. You can have different frequency ranges, right? And okay, line of sight, propagation characteristics of radio channels continued. I think I had, yeah, this is from here. We had ground waves and sky waves, right? But really, I mean, you can look at these, and they're kind of interesting applications, but they are very specific to certain applications. But really, the majority of the transmission that we do are airwaves. They just go across the air. And for these kinds of channels, we have two basic types of channels. We have line of sight and non-line of sight. And this is mostly for communication above 30 megahertz, which is the majority of cellular communication internet communication and so on. Need little or no obstruction. They're limited by the horizon. So line of sight means you can see, the receiver can see the transmitter. Okay. Non-line of sight is you can't see the transmitter. And yeah, I've taught a class on sensor networks, and I was looking at different papers on the topic, and one of them I ran into was a conference paper, and it was so sweet. There was a PhD student, and he made this sensor node, and he wanted to measure the amount of soil, the fertilizer they put in the soil, and the conductivity of the soil, how much water was in the soil, if it needed to be irrigated, if you needed to water this area, and so on. So he wanted to make a sensor network for this. So he makes this little sensor node and he puts it on the ground in the grass, and then he spends all this time and he can't get a signal, right? He can't communicate with this node. And finally he figures out it's because he has no line of sight. And all of the experiments he did in the lab, he had the sensor node on a table, and then the other sensor node it's transmitting to, or his laptop, is also on the table. He had direct line of sight. When he put it down on the ground, it was literally outside where there was grass, and the ground was soil, so it wasn't very flat and even. So it kind of, I guess, melted down into the ground a little bit. And what happened is he couldn't get line of sight to his laptop, and he couldn't pick up any information. And he detailed this in very scientific language. First, we went into the field. We attempted to communicate with the device 3 times. During this communication, we found no signal. I mean, it's just very long, just explaining this. And finally, he gets to the point where he's like, well, we figured out why. It was because of all of the vegetation and the grass. So non-line of sight channels are very difficult to communicate across, because you might get a signal, but only if it bounces off something else. I guess in a field, he didn't have that either, right? He didn't have a shed or a car or something, signal go there and then bounce back to the laptop. That didn't happen. So that's what you hope for in non-line of sight. You can't get line of sight. It should bounce off something else and get to your receiver. That can be an advantage or a disadvantage. And then there's other channels like acoustic channels that work differently. Acoustic channel is acoustic communication. I'm not talking about voice. This is high frequency, higher than the human hearing. And they use this for underwater communication. Apparently it disturbs the whales. That's so they're trying to not use it so much. But it's also a method to communicate. Okay, so speed, wavelength, and frequency. So this says AC current wavelength is 5,000 kilometers. But like I said, even at 500 kilometers, you're going to run into some trouble on your system. FM radio is 3-meter wavelength. Cellular has 37.5. Satellites get to 20 gigahertz. Not even satellite anymore. This is going to be regular transmission now. The kind of old source here has 15 millimeters. And the good news about this is you can have more than one antenna. You can smaller antennas for your cell phones, and you can have more than one antenna on your cell phone, and it won't take up space as you go high in the frequency range. And this is another chart. This is kind of old again. Like UHF television doesn't exist anymore, but I like the figure. Okay, so we've kind of run out of time. I was going to show you something else, but I will just very briefly talk about one thing. In communications, we're interested in the probability of error. And the probability of error is number of bits that you receive that are incorrect. You have mistakes. You send a 0, you receive a 1. Or then you send a 1, you receive a 0, divided by n, which is the total number of bits you send. You can tolerate some error here, but not a lot. And how much error you get depends on what's called the signal-to-noise ratio. The signal-to-noise ratio, I don't know if you've heard this, people use it in regular life as well. Oh, the signal-to-noise ratio was high. I mean, signal is important information that you actually want to receive, and the noise is everything else, including different sources. It's expressed in decibels. We'll talk about that one time, maybe next week actually. Transmitter, I'm not going to go into these. I want to look at the sources of noise. Okay. Terrestrial, mostly lightning in HF. Extraterrestrial, mostly the sun for VHF through microwave. You get a lot of, just the background radiation, sun radiation. And there's a lot of man-made frequencies. For instance, I talked about this with the microwave. The microwave is causing interference to your Wi-Fi network. But machines, any type of motor makes a lot of frequency, like they just randomly can just produce noise, electromagnetic noise at different frequencies. There's a certification process to stop the noise, to show that your product doesn't produce so much noise. But you know, if you have a really big motor or something, it's very hard to stop all of the noise that it's emanating from this electromagnetic system. And of course, thermal frequencies. This is thermal noise. Thermal noise is the random movement of electrons inside a wire. They just like move around for no reason. Quantization noise, because you only have a finite number of bits on the computer, right? You can write 10.1115, you know, you can only go to a certain, and then the rest of it you have to truncate. So this is about storage. And you know, circuit noises as well, and circuit interference, self-interference in the circuit. This is actually the biggest cause is thermal noise. So every type of communication has thermal noise. And the thing I was going to tell you was thermal noise is the biggest source of noise. Other sources of noise do exist, and they are also problems. Depending on your frequency, they may be more important or less important, but usually they're less than thermal noise. But noise is limiting for something like space communications. Oh, I've gone over time. But anyway, let me finish this. Space communications, thermal noise is important because you're transmitting across long distances to a satellite, right? So your signal becomes very small. So your signal to noise ratio becomes very, very small because your signal power is so small. The noise at the circuit becomes very important. Even a small noise can stop your signal. But when we talk about cellular communications, for instance, or Wi-Fi, your biggest problem is not thermal noise, it's interference from other users. If you have one of those Wi-Fi apps that looks at networks, you will find, like in my area, there may be 15 Wi-Fi networks, and there's only 5 channels. Okay, so, and the same is true for cellular communications. Interference is really, for us, a much more limiting thing than noise, you know, circuit noise or yeah, this is another one, circuit noise. But circuit noise and thermal noise become just too small unless you're communicating out into space, and then you're probably the only user. And so the important thing is the power of your signal. Okay? Any questions? I don't know. I'm not reading. I didn't even ask you any questions. So this midterm, I'm not reading. And we will try to get it done as quickly as possible. You know, we've had some, I've had issues. I'm sure my friends have also had issues coming up in this time. So yeah, we're trying to finish it. Yeah. Any other questions? Hamza, yes, you can talk.
Hello.
Hello.
I would ask if there is a second midterm or just midterm one and the final.
I believe it's a single midterm and the final. You can also look on the syllabus on the main website. Let me see if I can show you.
Yeah,
Okay,
I know it.
yeah. What it says there, I believe it
There's
says midterm, right?
just
Yeah.
midterm one.
Now I can't go to the other. I think I crashed. I'll stop sharing this. Maybe that'll help. I think I've crashed your program, guys. Hold on, I'll try to come back in. Okay. I just got a bump and I crashed.
I know it.
Oh,
see
I
the
can hear
syllabus.
you. Okay,
Yeah.
I can hear you guys. My browser has crashed, so I can't see the comment section. Whatever you say, just open your microphones and say it. It's okay. Whatever the last comment I could not see. Let me tell you that my browser has crashed, so I don't know how much longer it's going to stay up. I'm going to close the program and log back in. I think. Oh no, it's coming. Nope. Okay, I'm going to close the program. I'll log back in. If you guys have any more questions, I'll ask you in a minute. Okay, I'm back. This is a big mess. Sorry about this. I'm transmitting from the toy area of the house. But okay, so did you guys have any more questions? Yes, I can see your messages now. Yes, and Anas has a question? I can't see the messages from before. My messages. Oh, well, thank you very much. Can I stop a signal with another signal, such as let's say, yes, you can, but it's very tricky because the phase changes as you move, right? Like I said, about this the spatial wavelength or spatial frequency. It's if it's peak signal in one place, it's bottom signal in the other place. So you basically jammers generate a strong signal at all frequencies that can basically drown out any other signal. It's like talking over somebody else so they can't talk. That's the way most jammers use. You can kind of try to pinpoint it, but it becomes an issue of where it's constructed, where it's distant. What are you going to next year? Second year, yeah, right? Sophomore, junior, senior. Yeah, second year. Okay, so you study. Haven't you seen the program for this? If I go to, I'll share my screen in a minute. Let me pull out the mechatronics engineering. Are you mechatronics or electrical? Yes, yes. I upload the first set. I will upload the second set as well. Yes, absolutely. If you haven't seen this, this is mechatronic engineering. I can also hold on. Let me share my screen. I can also show you the electrical engineering syllabus. It's a little bit different next semester. This is for mechatronics engineering, but a lot of the first semester classes are the same. Math 3, circuit analysis. Math 3 is linear algebra, by the way. It's very easy. So you have a nice math year next semester. And I think 4 is easy too, because it's a lot of memorization. Math 4 is the second semester. You'll electrical and mechatronics. We'll do computer analysis, circuit analysis, computer programming, computer-aided technical drawing, engineering mechanics, numerical methods. The engineering mechanics for mechatronics. The electrical people will have something else. Okay, hold on. I'll send you mechatronics. Okay, perhaps introduction and mechatronics are the same lesson. Yes, right now, yes, they are, because we merged them. No, he's asking about the syllabus. What are we going to study next year? So I'll put up this a link to the syllabus as well, so you have it. So this is specific to mechatronics engineering. Electrical engineering, take another circuits course or something. I forget. Yeah, this one's for mechatronics. And then you have signals and systems. This is both electrical. All of these 3 courses, second semester of sophomore year, are the same for electrical and mechatronics. Oh, and also electromagnetic theory. All 4 of them are the same for electrical and mechatronics. And you guys take mechatronic systems, and the electrical engineers take another circuits class, circuits and systems. Okay, so I think they take another circuits class here the first semester as well, I think. So yeah, it's very similar for the second year as well, for mechatronics and electrical engineering. No problem. Okay, see you guys next week, okay? Take care. Have a nice day, you too. Bye-bye. Yeah.